which sorry, no worries. Which accounts for 80% of the total mass of the dark matter. The other 20% is in galaxies and in the ICM. One thing to note is that it's hot enough that and collisional enough in the core where you have Bremsstrahlung X-ray radiation, so breaking radiation, which increases in intensity towards the core. And what that gives you is significant radiative cooling. So without any sort of extra heating mechanisms, without anything else going on, this is enough to cool and collapse the inner core of the ICM within Hubble time, so roughly the age of the universe. So star formation in the central dominant galaxy in the middle is nowhere near bright enough to be consistent with an inflow like this. And we also see a temperature gradient. So we've observed temperature gradients that could not have lived if all of this gas was inflowing. So there must be some sort of potential heating there. And so there have been historically two mechanisms. One is thermal conduction into the core from a cooling radius, right about here. And the other is heating by an active galactic nucleus, so a supermassive black hole in the middle of the central dominant galaxy that you create some cool gas and it feeds back. So either by jets or other stirring, maybe buoyant cosmic rays, something like that, that energy is thermalized and feeds the core. Others had speculated that thermal conduction was also a potential, but there's a big problem with this in that the heat flux of just classical collisions is very, very temperature sensitive. So it's like temperature the sun has, meaning that you need a much smaller heat flux. You need something that is stopping this heat conduction in order to explain the temperature gradients that are seen. So what reduces the thermal conduction in the ICM? Well, it's not just a plasma, it's a high beta, highly magnetized weakly collisional plasma. So beta, or the ratio of thermal energy to magnetic energy, is somewhere in the hundreds. It's weakly collisional, meaning that the electron moving through path or distance between scattering events over the temperature gradient length scale is something like 1/100, but the electron diode radius is absolutely tiny. So the ratio of that to the mean free path is something like 10 to the minus 11, which is incredible stress separation. So what this means is that all of your transport is highly anisotropic with respect to the magnetic field. So parallel transport is strongly favored over perpendicular transport. And what this also means is the geometry of your field really starts to matter. So if your magnetic field is parallel to a temperature gradient, you have rapid heat conduction. And if it's perpendicular to, you can highly suppress that, the heat flux across the temperature gradient. So cold fronts, for instance, when you have field line draping over a temperature gradient, and also field line tangling can geometrically reduce your transport because it just mixes how electrons are able to move parallel to a magnetic field. Transport can also be mediated by kinetic instabilities on scales of the gyro radius. And these kinetic instabilities, generally in high beta, kind of come in two flavors, two popular flavors. So the first is like fire hose and mirror. So the free energy there is in pressure and isotropy. And then there are others, the Whistler instability, where the free energy is actually in the heat flux itself. So this is the one that we're going to focus on today. Right, so the heat flux driven Whistler instability, or HWI, can be explained as follows. So the cold plasma dispersion relation, your frequency is held as a parallel as a normalized to your gyro frequency, where D here is the skin depth, which is related to your normal radius by a factor of beta, square root. And so the waves have a certain phase velocity associated with them. which means that resonant interactions can occur when the frequency of the wave is 0 in the frame of your particle. So a wave and a particle can strongly interact when that is true. And for whistlers, this means that the the resonant parallel velocity mainly scales as k rho v over this beta plus whatever whatever the number is for your gyro resonance over k parallel. So given a magnetic field, let's call it in the x direction, and a heat flux, parallel heat flux in a weakly collisional magnetized plasma, this gives a or implies a certain distribution function, meaning you have your normal Maxwellian, but then there's a perturbation to that Maxwellian, which is proportional in size to how well your scaling. So if you are very weakly collisional, this can be smaller. So right, and this follows from other arguments that we will get into in a little bit. But when this term is sort of greater than your magnetic over thermal energy, meaning 1 over beta, you can actually drive gyro-resonant interactions here, and you can drive Whistler growth rates that overcome cyclotron damping that results from the core. The only limitation is the exponentially small numbers of electrons at high V, which also gives you a cap on your growth rate as a function of K. So we ran a number of simulations, 2D particle and cell simulations. So particle and cell PIC code we used was Princeton MP, which stands for Spitofsky's. And we set up a 2D box, essentially a very elongated 2D box, parallel to a mean magnetic field V naught, with a width of just 25 rho e, but a length of 125, 250, and 500. In the perpendicular direction, all of our boundary conditions were simply periodic. So a particle or a wave passes through the wall and it comes in the other side. But that wouldn't work for the parallel direction. So in order to enforce a heat flux in our box, just to drive this instability towards a saturation point, we fix the temperatures of each of the walls. So anytime the particle hits the wall, it gets resampled at a certain Maxwellian of these two temperatures and then re-emitted back into the domain. So we initialized a linear temperature profile from hot to cold. All of the runs were T hot over T cold 2. And we initialized 2 different types of equilibrium. One is a pressure gradient lifts equilibrium. So that also means that your plasma beta is constant throughout the whole box. But it's simple, but it's not really physically well motivated, because what you need is a temperature gradient and a density gradient that are anti-correlated to each other, which doesn't usually happen in nature. So we also included runs with a gravitational term balancing the pressure gradient, a much more natural setup. And we just went and did a whole spectrum of runs. So in between beta 10, 25, 40, 50, and 100. And we also increased the length scale, so meaning that the temperature gradient length scale is also increased. Or we also did a spectrum of those runs. And it'll become clearer later in the talk why exactly we did this, but this is just to get a better astrophysical scale calibration. So we're pushing these runs kind of a lot, and we want to make sure that the results that we're getting are applicable to larger astrophysical relevance. And we ended up tracking about 500,000 particles, so per species, a million total, at 10 times the gyro frequency. So, and I'll just mention why didn't we go bigger or higher beta? The cost of these things scales pretty tough with the both the area, the size, the length, the time of the run, but also beta to the 3 halves. So going much higher really ended up costing a lot, and our traditional simulations even already a little less than 1 million CPU hours. So number of results here. Every simulation has essentially 4 phases. So our initial equilibrium is a local Maxwellian at every location along the temperature gradient. So it takes about 100 cyclotron times to establish a heat flux that gives you a perturbation in your distribution function that is strong enough to excite those waves. So once that happens, you get a small amount of exponential growth. So delta B scatter increasing like an exponential to the t. But once your scattering rate, the actual rate, once your particles start reacting to that fluctuating magnetic field, the growth rate actually drops to secular growth, meaning it grows linearly in time. And then after quite a long time, you finally achieve saturation. It's part of another reason why these simulations are so expensive. So
Could I ask you a question on your previous slide?
Yeah.
So I'm looking at the time, I mean, after 10 to the 2 cyclotron periods where you end the exponential growth and you enter this power law growth. So delta V over V naught is growing there, but it looks like your heat flux is decreasing. Okay. That's, and then eventually the heat flux saturates, but do you see saturation in the delta V over V naught?
Yeah, for I haven't included them here, but for our our larger scale separated runs, you go long enough, you end up seeing it. So it just takes a really long time. One of the good things about doing this is that all of your scalings happen like power laws. So if you decrease or increase your let's say beta or temperature gradient length scale by, I don't know, a factor of 2 or 4 or whatever, that how those scale as functions of these parameters, you get very little noise within those actual numbers. So even though some of these weren't run to complete and total saturation, we're pretty confident with the scaling. So what we ended up finding was that the heat flux is actually suppressed quite significantly. So for every increase in beta, that heat flux was reduced by that amount. And accordingly, the magnetic field fluctuation amplitude also scaling as beta over the temperature gradient length scale. And these have been found before in previous work. So in the late 90s, Princeton and Eichler did an analytic paper where they used a quasi-linear argument to suggest that Whistler's act as pitch angle scattering centers for electrons. And once the rate of scatter roughly equaled the growth rate, which is proportional to beta, the perturbations to F would be limited to 1 over beta, so you'd have this heat flux scaling. So concurrently with another work by Komarov in 2018, who cited Princeton and Eichler, kind of confirming their work, Robert Clark and Drake and a few others ran a number of similar simulations, but their explanation is different. They suggested that Whistler's acted as mobile scattering centers that convected the energy down the temperature gradient at the whole plasma at the phase speed that was suggested by the cold plasma formulation, rethermal and beta. And then there was follow-up work saying that by Drake in 2021 that the Whistlers acted as pitching the scatterers in the frame of the waves. So There was previous evidence for this from one of the Rover-Clark paper. There's very little change in magnitude of energy, and these are scattering more or less on isocontours of velocity, meaning the pitch angle scattering is a good approximation. However, a lot of these previous computational studies had limited scale separation, and this was for good reason. I mean, these simulations can be pretty prohibitively expensive, depending on how you set them up. And so part of our motivation to do this was going to higher scale separation to test the asymptotic behavior as delta B over B got smaller and away from 1. Because a lot of things can happen when your delta B over B is 1. You can start trapping a lot of electrons, if scattering even look diffusive anymore. And does the scaling really continue to apply to astrophysical scales? So I think the reason that a lot of previous authors had said, okay, this has to be some sort of diffusive flux, is that what you get from these equations is consistent with that. But ultimately, this consistency is not an explanation. It's so we went further to try and explain. So just to recap, we have a scaling for Whistler turbulence in both beta and temperature gradient length scale. And while this is consistent with a diffusive flux, it doesn't confirm that. And so we want to take these large, highly driven simulations and try and get them to a regime where it's more realistic, so to speak. And then confirm what the physical explanations are, right? Does the quasi-linear theory used to explain the scaling, does it apply to our runs, and do our runs apply to the large scale, realistic scale? So to investigate this, we used a number of independent methods to actually obtain a collision operator. And I'll just talk about what that means in a minute. First is the Chapman-Skog, then a quasi-linear approach, and then a Fokker-Planck, and we'll get into each of these in turn. So one piece of background is, so if you have a kinetic description of a plasma, how do you get a fluid description? So the kinetic description of a plasma is all baked into the Maxwell equation. So the rate of change of a distribution function, meaning how your particles are distributed in time, space, and velocity, flows along this derivative here. So particle in time, how it responds to gradients in space, and then responding to your electric and magnetic fields. So the rate of change of this along this conductive derivative is 0 except for collisions. And so we are looking for how we're essentially deriving a model for what these collisions look like in some sort of spatially averaged sense here. So you can rewrite this in terms of the peculiar velocity. So the fluid velocity is this u here, which is the one we all know and love. And then, so taking a bunch of derivatives and expanding them, you find that this equation up here can be rewritten where this term over here is corresponds to rapid gyro motion of a particle around the field. And this material derivative here is the classic one you know and love from fluid dynamics. So then what do? You take moments of this, meaning integrate with respect to the peculiar velocity this entire equation. So the 0th moment gives you the continuity equation, so mass conservation. The first gives you a force equation, so how your bulk velocity or your fluid velocity moves in terms of electrokinetic fields, pressure gradients, and drag. And then you can keep taking higher and higher moments to get entropy or energy equations, yada, yada, yada. So where does this stop though? None of these variables, so for instance, heat flux, you would like to put in terms of density, pressure, energy, these sort of things. This setup doesn't tell you how to do that at all. It doesn't give you a sense of what thermodynamics looks like. So in order to get basically thermodynamics out of these equations, you can assume that you have a small parameter. So in our case, a small parameter is both the mean free path and the gyro radius. Assuming that's small relative to your large scale gradients, this implies a time scale hierarchy where you have kinetic physics happening on a rapid time scale, more rapid than your sound crossing or force balance time scale, and even more rapidly than diffusion. And this can be leveraged to close the whole fluid system. So you go in, you expand your kinetic equation in these variables, and then you can determine what your lower order distribution functions are algebraically in terms of, sorry, you can get your lower order ones in terms of your higher order ones, so on and so forth. So substituting in our force equation for into this Maxwell equation. So to lowest order in that small parameter, you just have that the effective gyro motion and your collision operator on your zeroth order distribution function needs to be zero. So one other complication in this is that you want to pack all hydrodynamic information into your F naught to make the perturbations to your general distribution function purely kinetic. So you want the first, second, and zeroth, first, and second moments of your distribution function to be zero, of your perturbed distribution function to be zero. So then to first order, assuming that your pressure and isotropy pi over here, your drag, those are all small and beta, and all of your flows are highly subsonic, you can take those terms out and you get what's called the correction equation. And this correction equation is what actually gives you your higher moments in terms of your lower ones. Right, so for our Chapman and Skug operator, we are assuming that whistlers are acting as pitch angle scatterers in a frame moving at the wave phase velocity. So the collision operator, you can see here is the pitch angle derivative, where xc here is the cosine of your pitch angle, meaning the angle between your magnetic field and the particle velocity. With a factor here and your scattering frequency, and also in terms of that. So you can expand this equation back into the lab frame. And assuming that the Whistler phase speed is border everything else that you assume is small, you will pick up a drag term. It's the same order as diffusion. All right, so here we go. This is the real thing this time. At order zero, you have, okay, gyro motion plus your pitch angle scattering has to be zero. The only way to satisfy this is that if your F naught is just a function of velocity, so it's isotropic. Okay, and then at first order, gyro averaging your correction equation, you are left with parallel transport. And so what you find, and this is that parallel derivatives of your Maxwellian or close to give you what your perturbed distribution function should be. So you can rearrange and integrate this to find what your implied scattering frequency is by some measured F1. However, this is sensitive to what your actual Whistler phase speed is. So we went through and
one question for you. On your previous slide,
yep,
for your conclusion about F naught, is that supposed to be C prime and V prime? And you're having F E naught is isotropic in the frame of the Whistlers?
So no, so it's a zeroth order in epsilon, assuming that the phase speed is small, you recover pitch angle scattering in the lab frame.
And then, okay, so in the lab frame or in the frame of the mean flow U? So
Yeah, okay, yeah, so technically mean flow U, I'm ignoring this because of, what we did back here. Right, so yeah, assuming that these flows are small, and taking, right, assuming that those flows are small, I can sort of replace that W with a V. Yeah,
okay,
this is just I had to do her a little bit through that. We have no, well, highly stubbed Whistler phase speed bulk flows in our simulations. So U is subdominant to any other velocity you're going to see in these calculations. Okay. Okay, so cold plasma Whistler dispersion gives the phase speed as V thermal over beta. But we went through and we actually did spectrograms of our simulation. What we found was that the phase speed was actually slower than that by a factor of a fifth. So on the right here, you're seeing some like actual spectrograms of the perpendicular fields, but it's By plus IPC. And what happens when you do a spectrogram of that is that you actually get the handedness of the wave to come out. So power in a negative frequency here corresponds to right-handed waves, and power in positive to left-handed waves. So the Whistlers here being right-handed, there's only power for K parallel, KY, so K perp 0, and then there is some power in left-handed modes, and this just has to do with the obliquity of the waves as you change their wave vector. All right.
could I ask you another question?
Yeah.
That velocity 0.2 V thermal electron over beta E, how does that compare to the alphanes?
Well, it depends on what your beta is, right? So if alphane is like V thermal over root beta, then let's see, yeah, I guess then there's an extra factor of the square root of beta in there. So I think for beta greater than 10, this should be.
I guess I'm just wondering, is it possible that could be an alphane mode or drive that in a Whistler mode?
I think yeah, I mean, for beta small enough, yes, probably. Right, but as you increase beta, this, the way this scales is much more shallow than your alphane velocity. So this factor of 0.2 could be potentially an issue at beta of 10, something like that. But as beta goes to 100, yeah. No, yeah, I see what you mean. It's a good point. We had not thought about that, but yeah, assuming that for large beta things are scaling like this rather than so moving on to numerical results. So from a restart done to our simulation, we can determine what the distribution function is. So taking the 0th order distribution function at the single average, with the first order change to that being F minus F naught, this ensures just by definition that all of our hydrodynamic information is in F naught, all of our kinetic information is in F. And the only caveat being that our derivatives here, you'll note that this term has a 1 over dF1d pitch angle in it. And this ended up being quite noisy. So we were only really able to get velocity information out of this instead of full velocity pitch angle. So what we ended up doing was fitting a model to this data, the model being a slow and a fast power law in velocity. So slow scattering rate with a slow power law, and fast scattering rate with a fast power law. And you can see the data from the simulations is in the solid here, and the fit is in the dashed lines. And so you find relatively good agreement that your fast power law is both fast and slow power laws are roughly constant, but the scattering rate for the fast particles increases with beta, decreases with LT, as you would expect. And the slow actually kind of tops out to right there. And this gives you a model for your scattering frequency. So does this actually explain what we see in the simulations? You can go and calculate this. So for an operator that looks like this, you can calculate what the implied heat flux is for that operator by running this back through the correction equation and calculating what your perturbation to your distribution function should be. And it actually gets quite close. This model is very predictive. It's kind of predicted by construction in the sense that we required our scattering rate to explain the heat flux. So, however, it is at least simple, right? So we have a simple model for what our scattering looks like, and that's definitely helpful. So we can also construct a quasi-linear operator or something kind of like a quasi-linear operator. So this is constructed from what you expect your resonant interactions to look like at every point in velocity and wave phase space. So assuming a pitch angle operator with a scattering rate that actually depends on your magnetic spectrum and then what the resonance condition is. This W sub B here is the power spectrum of the magnetic field. You can make some reductions to this equation up here, and that the Whistler wave phase velocity much smaller, so gyro resonant interactions don't care much about what the phase speed is when the phase speed is small. And then the other complication being that you need to treat this delta function here, which is the resonance condition, very carefully when you do sums. So in doing this, what we essentially found was a good fit to the quasi-linear operator scaling as some power of V parallel. And this is sort of demanded by the form of this operator here. And in general, the fit is a good fit for V parallel 2.3. And this implies a spectrum of minus 3.3, which given the noise in our spectrum is a possibility, not, I wouldn't say definitively not 3.3 or 3.3. Just to note, the scalings for kx rho e and ky rho e greater than 1 are roughly explained by k to minus 4. This is consistent with other work with particle in cell simulations where they have a cascade past the gyro, past k rho e 1. So we can go and we can fit this again. There are error bars on this, I promise, they're just really, really small. So the analytical form of the quasi-linear operator demands a scaling like V parallel to 2.3, but also a scaling like beta to the 1.4. So the explainability of this model in particular is not superb. And so we can also see that when we calculate the implied heat flux, it disagrees with the actual data. And for real astrophysical betas and analyses, this would probably not explain or not be an accurate representation of the heat flux observed.
Sorry,
Yeah.
the actual data in the blue dots.
Yes, yes.
So the first method is the green one, and then
Yeah.
it's just.
Yeah, so just to repeat, this is the actual data, the blue dots. The Chapman and Scott operator are these green X's, the quasi-linear here are the red. Okay, so finally, our third method here is a Fokker-Planck type operator, and this is kind of the heavy-handed, most easy to misinterpret of the operators. So what this is you essentially assume that the rate of change of your distribution function is caused by both drag, represented by this grad A term here, and diffusion, this B term. So in our velocity, pitch angle, and gyro phase coordinate system, what you have is drag and diffusion and velocity, drag and diffusion pitch angle, and then number of cross terms, which we will ignore because they end up being orders of magnitude smaller than either the velocity or the pitch angle terms. So the way that we actually get these coefficients from our simulation data is by measuring Lagrangian jump points. So for every electron that we track, we can take its velocity at any point. And we know, given delta t, what that velocity of that particle is, so we can subtract it. And so assuming that these jump moments are small, you can calculate what your drag and diffusion coefficients should be just by summing them up over particles and then binning them in phase space, in real estate. The one issue with this is that whenever you see definitions for Fokker-Planck operators, you're going to see this delta t goes to 0. And when you're doing analytic calculations, and the only time scales are the collisional time scale, that's fine. You can just take delta t goes to 0. But in real life, we have an autocorrelation time scale. So this is how long a particle interacts with in a correlated way with the force. So if it's wave particle interactions, you can estimate this as the quasi-linear autocorrelation time. So the time an electron takes to interact with a coherent wave pathway. Assuming a wide spectrum, which know we have, centered around here will be roughly 1. For large beta, you find that your autocorrelation time is like a cyclotron time. So with sort of low scale separation, so your scattering time kind of sitting a little bit on top of your autocorrelation time, and high magnetic fluctuations, we derived a model for what our jump moments should look like to make sure that we are doing this method correctly. I'm going to what this means in a second. So in general, you can solve the Fokker-Planck equation. And if we just take a simple pitch angle scattering operator with a constant frequency, you can rewrite this in terms of drag and diffusion. This equation has a Green's function solution, which can just be written as a Gaussian in terms of your jump moments. And what this means is that when you sample a bunch of jump moments from your code, you should expect that these have this distribution in both time and jump moment. And so you can run the calculation through and you get exponential dependencies of these coefficients with your jump time. And this applies for any variable. So this is it's a prototypical statistical process where drag and diffusion both interact on the distribution function, called Ornstein-Uhlenbeck process. This whole thing is well known. And it gives us a standard by which to choose a delta t from our data and check that our statistics match this behavior and are consistent with these results. So note that you can actually expand these and recover what the Fokker-Planck coefficients are by doing expansion in small delta t. So everything is consistent. Right, so because of this limited scale separation and the fact that our first and second, well, our drag and diffusion coefficients have strong dependencies in both velocity and pitch angle, we had to produce a number of these at different delta t's. And then at every point in phase space, you have to use what these are as a function of delta t to actually derive what an appropriate jump time is. So for instance, our largest scale separation run, these are the first, drag and diffusion at delta t omega e is 10. And so if I take the point at this x, and I then instead plot it as a function of the jump interval, what you get are these curves, and these curves are exactly what you expect from this calculation here. So what this ends up meaning is that for each one of these curves, exactly where this transition point happens from constant to scaling like 1 over delta t is roughly where your collision time is. So it is where delta t times your collision frequency is 1. So going through all of these, you can select appropriate delta t's, and at larger and larger scale separation here, which are these decreasingly or increasingly pale blue lines, the scattering frequency increases, your scale separation increases, and so you have sort of more freedom, so to speak, to pick your delta t. So if we go and we do that, I picked a subsample of pitch angles here, and we take an appropriate delta t, we sample our drag and diffusion at those delta t's. We can again fit a good, we have a good fit to our fast and slow power law model, except that now we have our scattering, well, at this time, our diffusion coefficients as functions of pitch angle themselves. So if I do this for every one of our runs, we'll note that the actual pitch angle shape that we get every time we do this doesn't converge to a value. This is what we would have liked to see, because if this converges to a value within simulations, we can be more or less confident that as we go out to astrophysical scales, the operator will actually have this shape in pitch angle. The problem is we didn't quite get there. So instead, if we just do a pitch angle average, we end up finding roughly a scaling of beta and 1 over LT, although the fits are not really as good as each other. So, and one reason for the change in shape is in fact what I was alluding to earlier, the strength of our fluctuation. So within a certain jump moment, what you're seeing here are PDFs of our jump moments here. So what we would like to see is something that looks like a Gaussian, where the Gaussian fit to these, not fit, the Gaussian with the same mean and variance as these measured distributions, the solid lines, are in dashed lines. And so beta 10 and beta 40, this pale blue here, are our largest, our smallest delta B over B, either gone by going to low beta or high LT. And those are beginning to approximate what our ideal statistics actually should look like. But for everything else, we're kind of just getting a wash. And so what this means is that any structure in pitch angle is actually getting at low delta V is kind of getting smoothed out and pushed around as a function of pitch angle. So hence we take the pitch angle average, getting a very similar operator, at least in the fast power law, to the Chapman and Skog method used before. So only difference here is mostly the flow power law. I run this through the implied heat flux again, and plotting in purple this time the Fokker-Planck results over the old results for the other two, consistently overestimating the heat flux. So even though we know a lot more about what's going on, the Fokker-Planck method might be a little too heavy-handed. So to sort of sum up where we're at, Chapman and Skog, simple, easy to calculate. You need to assume a form of the operator, but once you do that, you can explain your transport with the model you get for that operator. The one thing I will note is that it is sensitive to F naught. So if you don't have a max line and you have something that looks like one, you can really kind of start to mess up what your implied heat flux is from there. The quality linear approach, also easy to calculate. You just use the spectrum of your fields. It's physics rich in terms of explanation, but by definition also doesn't give you scattering as V parallel goes to zero, or technically, I guess, as V parallel approaches the phase speed of your waves. The Fokker-Planck method, very expensive to calculate, but very powerful, but can kind of lead you astray if you're not willing to kind of swallow all of the technicalities that come with it. So at the end, we're sort of left with this general approximate operator here, consistent with the Chapman and Skog results. So we do have a diffusive heat flux in the frame of the Whistler, which can be approximated by the pitch angle scattering operator with this collision frequency. So a good question to ask is, when is this appropriate, and when is this useful, and why did we go all the way through this? I mean, although we didn't converge to an operator, we have good explanation power in the Chapman and Skog method. So trying to obtain what a collision operator looks like just from the spectrum alone could lead you astray, and probably more detailed methods there will get you closer. But we hope it's at least a good reference, a good starting point for anyone developing a methodology to properly measure collisionality. But it's also useful for the ICM and global scales. It's a little bit marginal, but any scales, any temperature gradient length scale smaller than that, this collision operator should begin to dominate. And that has strong implications for essentially any heat flux buoyancy instability you might have. So there are other larger scale instabilities where rapid conduction along field lines is actually feeds the growth of that instability. So another final conclusion here is that the temperature dependence of the heat flux, if it is Whistler mediated, is much softer in temperature, and so could be a better fit essentially for our observed temperature gradients in ACM. And do a final note on, okay, so it seems like we're getting better every time we increase temperature gradient length scale. Why did we not just do that, right? Well, the cost for our fiducial run was just under 1 million CPU hours. And the scaling of this is pretty brutal. So if we wanted to get our delta V squared, to 0.1, much lower, we would have to increase our temperature gradient length scale enough where it would already cost 10 million CPU hours. Our PPC as well is actually relatively noisy, so we would likely have to go to even multiples of that. So a well-resolved kinetic simulation giving you well-resolved transport is exceptionally expensive and probably won't have it for a little while. But there is another way, and this is some future work that we're working on with Matt and Archie. There is supposedly a ion analog to the HWI. It's supposed to limit heat flux in the same way, and could be important for low luminosity accretion flows where your temperature ratio of ion to electron could be high, approaching the mass ratio, square root of, square root. So preliminary simulations of this using a hybrid kinetic code, which is MATS, where you treat electrons as a charge neutralizing fluid in a fixed simulation. We've run a couple of these and have started to find some good results already. The cost scaling is much more forgiving. There are fewer scales that you need to resolve. For instance, the cost doesn't scale like beta at all, which is helpful for us. So I'll just end there by saying thanks for your attention and thanks, Ben, for inviting me.
Is there any questions? Maybe.
Yes, with regard to your last point, what exactly is different about the physics of the Whistler instability versus the slow mode instability that drives the unfavorable scaling and the Whistler instability?
So that just comes down to how the simulations are done. So in a full pick simulation, you need to resolve the Debye length. And so you can kind of do that by getting the thermal. So you need to resolve the Debye length by at least, I think it's 1.6, something like that, cells. And so between that and your skin depth is V thermal over C. So you can only go so high there if you don't want relativistic simulations. And then root beta to rho E. So you have like 3 intermediate scales that you need to resolve to get a rho E by rho E box. In the hybrid simulations, you just need to resolve your gyro scale. So
Right. So it's basically rho E versus rho I.
Yeah.
Or is there more to it than that?
Well, so the scaling is only in the cost of the simulation itself. So like for every rho E, you need to in a kinetic, fully electromagnetic kinetic simulation, you need, let's say, hundreds of cells, which means hundreds of particles per each cell. And so the cost of that starts to increase dramatically. And that the number of cells there also scales with your beta. In the hybrid simulations, all you need are a set number of cells per rho I. So there's no factor of beta I there, there's no factor of V thermal over C. So you can keep that constant as you increase your beta.
Okay.
You, and when you 5 slides back, mentioned something about when you looked at the Chapman and Scott method, you have to be careful about it being not, not swelling or not maximum. I was wondering if you could say a little bit more about what gives rise to that sensitivity. What's the effect involved?
Yeah, it has to do more with right here. So you end up dividing your F naught by some derivative of F1. So F1 itself is sensitive. The velocity dependence of F1 depends greatly on your velocity dependence of F naught. And so if you assume, like, let's say there's a tail on your F, and you assume that F is a Maxwellian, well, I mean, all of that tail, for instance, will end up going into F1 and give you velocity structures that don't look anything like what you would expect. I mean, at least for this, right? Sometimes you do want to have the tail be in your F1, but you know, just doing pitch angle here, all of that will end up being reflected in the power laws of your scattering frequency. And so you could get your scattering frequency going like, I don't know, E cubed or something like that, something dramatically more, which will give you a wildly inaccurate applied heat flux. Yeah,
That's finger speaking again.